The sun is rising, most definitely. A new day's coming. Ooh, people are changing. Ain't it beautiful? Ooh, crystal blue persuasion.
Okay, so Tycho Brahe, whose Earth-centered system we last considered, is widely regarded as the best and most productive naked eye observer in history. Now, Johannes Kepler, a German astronomer, was employed by Brahe for a few years before Brahe's death for the express purpose of doing the mathematical calculations that would prove Brahe's model correct. Kepler, however, was convinced that the sun-centered system was correct, and he profited enormously in his goal of proving this by inheriting all of the data Brahe had so painstakingly collected. So Tycho Brahe, whose Earth-centered system we last considered, is widely regarded as the best and most productive naked eye observer in history. Johannes Kepler, a German astronomer, was employed by Brahe for a few years before Brahe's death for the express purpose of doing the mathematical calculations that would prove Brahe's model correct. Kepler, however, was convinced that the sun-centered system was correct, and he profited enormously in his goal of demonstrating this by inheriting all of the data Brahe had so painstakingly collected. As you probably know by now, Brahe is long suspected to have been murdered, and Kepler was one of the prime suspects. However, recent evidence from experiments performed on Brahe's remains tends to suggest that he died of a ruptured bladder, rather than the mercury poisoning as originally suspected. Not nearly so great a story. Well, Kepler was a contemporary of Galileo, and like both Galileo and Copernicus, was someone on whom the basic facts of the Aristotelian worldview had begun to lose their purchase. And toward the end of this chapter, DeWitt gives a rather lengthy account of Kepler's strange conviction that God had positioned the orbits of the planets relative to each other in a way that reflected certain profound geometrical truths. That's what's being depicted in the video at the beginning of this screencast. It's very interesting to think about that Kepler actually thought there were reasons why the specific planets themselves were in the positions they were in. We can call it strange, but we've already learned that there was nothing remotely unusual about the tendency to imbue the basic mathematical and geometrical facts of the universe with mystical significance. DeWitt says that Kepler was motivated by the desire to read the mind of God. But that's probably how most scientists of the time would have understood what they're trying to do, and how some today still do. After all, if God really is the author of the laws of the universe, which everyone believed at the time, then this view makes perfect sense. And assuming God is supremely rational, then this was a very powerful incentive to believe that there is a fundamental and discoverable order in the universe. It's worth reflecting on the fact that humans did not come by this conviction easily. For most of our history, our experience taught us that the world is fundamentally unpredictable. The Greeks, for example, explained events in the world by reference to the selfish and cruel whims of the gods. These were teleological explanations. After all, they made reference to the purposes of the gods. But they were explanations that denied any hope that the future was something within our power to predict or control. Well, Kepler's basic innovation can be so easily stated that it tends to mask what an incredible step it represented in the history of our understanding of the heavens. Basically, Kepler just gave up on the perfect circle fact, and the uniform motion fact too, as it turns out, and began to explore other possibilities. What worked in the end was an ellipse, an oval or egg shape, which bears the same relation to a circle that a rectangle bears to a square. In other words, a circle actually is a special kind of ellipse, just as a square is a special kind of rectangle. No need for an apostrophe there. Kepler proposed 3 laws relating to elliptical motion, all of which turn out to be roughly correct. So the first law says that planets move in elliptical orbits with the sun at one of the foci. So let's make sure we understand that. Now, DeWitt explains how to draw an ellipse using a couple of pushpins and a loose string. And this video shows that way, as well as another way that represents an ellipse as a projection of a circle. So what's useful about DeWitt's way of drawing an ellipse is it gives you a good feel for the importance of the foci, which otherwise just seem kind of like 2 arbitrarily selected points on a line inside the ellipse. What the method illustrates, if you think about it, is that since the string does not change its length, that the sum of the distance between the foci and the planets always remains exactly the same. So in this illustration, you can take any triangle and sum the 2 segments of the triangle, say this one plus this one, and they will always add up to the same as, say, this one plus this one. And of course, this is true of a circle, except there's only one focus, or if you like, both foci are located at the same point, which is itself equidistant from every point on the circle. Now, Kepler's fundamental insight was that the orbit of every planet can be represented as an ellipse with the sun at one of its foci. It's worth noting here that the idea that some heavenly bodies travel in ellipses was not Kepler's but Brahe's, who had already attributed this type of path to a comet. So Tycho may have really planted the seed here for Kepler, and this is an interesting example of something that looks like a weird exception, the bizarre path of a comet, turning out to be the rule. It's also worth pausing once again to think about the perfect circle fact and the extent to which it's being undermined. Kepler himself has absolutely no idea why planets should follow elliptical orbits rather than circular ones. We had to wait for Newton to give any sense for why that might be the case. You could imagine that he might say, well, why not? The perfect circle fact is just bogus, and we do not need to explain why they don't travel in perfect circles. Well, that's maybe a slight overstatement. What does turn out to be completely bogus is the perfect part. That's true. The heavens turn out to be part of the material world, so the motions of heavenly bodies are no more perfect than the motions of earthly ones. However, a circular orbit is possible. And the interesting fact is that the orbits of all of the planets, except Mercury, actually are very nearly circular. Now, I say except Mercury because Pluto, as you know, is no longer regarded as a planet. Pluto's orbit was crazy. It was very elliptical, and it actually cut through the orbits of the other planets, which was actually one reason why it was demoted from being a planet. This is actually very surprising, given that a circle is just one of an infinite number of ways of making an elliptical orbit. One generous way of understanding the ancients is that they were trying to explain why, given all the paths they could be taking, the planets seemed to move on something very close to a perfectly circular orbit. And that turns out to be a very good question. You could Google that, and you'll see that there isn't any agreement today on exactly why that's the case. Kepler's second law, a line joining the sun to a planet sweeps out equal areas in equal times. So Kepler's second law can also be understood as less a refutation of the uniform motion fact than a sort of massive reinterpretation of it. At an observational level, the second law means that we will see the planet traveling faster when it's near the sun than when it's further away.
Let's go back to this image. We have that green object that's orbiting the big massive central object. Let's just call it a planet orbiting a star. So here my planet is orbiting a star at some initial time. We'll call it time 0. I'm going to draw a line between the two objects. This is the line that we are going to say sweeps out area. As this object starts to orbit around, this line will continue to move up and to the left a little bit as it circles. At some later time, we're going to give it an arbitrary 1 at the moment. We're going to say that the area that was swept out by that moving line is indicated by this dark purple region to go from 0 to 1. If I allow an equal time interval to pass, so if we wanted to say that that was 1 month of time, if I allow 1 additional month to go by, I'm going to sweep out some additional area. This time I'm showing that in the light purple. Kepler's second law tells us that the area swept out for both of these time intervals, the first time interval and the second time interval, must be equal. That's to say area swept out at a constant rate for a constant time. I can continue the pattern. Let's see what happens if we go 1 additional month. I can sweep out another some quantity of equal area. These things are not quite triangles, although they're pretty close to that. I can keep going. Here we are at month 4, month 5, 6, 7, 8. Again, every different region that I've swept out here we say must be the same area as any of the other regions because we're moving at constant time intervals.
Sometimes called the slingshot effect. It's a phenomenon we've utilized to bring rockets back from the moon. This is a nice summary of Kepler's second law from the physics department at UC Boulder. So the position of the foci of an ellipse are described in terms of their distance from the center. which you may not be surprised to learn is the eccentric or the eccentricity of the ellipse. So Kepler's first law actually implies that when the eccentric has a length of 0, the orbit will be a perfect circle. And Kepler's second law implies that when the ellipse is a perfect circle, it will have to travel at uniform speed. And that uniform speed will produce the uniform areas predicted in the second law. So, as is typical in science, a new, more powerful theory still gives credit where credit is due. In this case, it's neatly modeling and partially vindicating the facts of the Aristotelian worldview. And DeWitt omits a discussion of Kepler's third law, but it's actually very significant and it's not at all difficult to understand. So essentially, Kepler's third law reveals a constant relationship between the period of the orbit of any two objects and the distance from the object that they are orbiting. So Kepler's third law states a constant ratio between the period t of any two objects, A and B. Okay, so you got object A and, you've got object A and you've got object B, and this is the period, meaning the time it takes to make one complete revolution. And then you've got the idea of a radius here. Now the radius of a circle is a constant, but the radius of an ellipse is always changing, so this is the average radius of the ellipse. And so you've got the square relationship here. The ratio of these two periods squared is identical to the ratio of these two average radii cubed. So if you know the period and the average radius of the orbit of, say, Mars, and the period of another planet like Jupiter, then you can actually deduce the average radius of Jupiter. Or alternatively, if you knew the average radius, then you could deduce the period. Well, Kepler's third law shows that Kepler was the first astronomer, really, to create what for us would be considered systematic knowledge of the motion of the heavenly bodies. You'll recall that Ptolemy, Copernicus, and Brahe all treated these wandering stars as if they had minds of their own. Of course, they couldn't do anything they wanted to. They had to travel in perfect circles, but we didn't know how big the circle would be. And even though they had to travel in a uniform motion, we didn't know how fast that would be for anyone. That was pretty much up to them. So they couldn't derive anything unknown about the behavior of one planet from the known behavior of another. So as DeWitt notes, it's difficult to say anything that's both precise and true about the reception of Kepler's system. In some ways, this is because it was delivered so all these taken together, the replacement of the perfect circle, the replacement of uniform motion, and the creation of an actual system of planetary motion, make Kepler's achievement the conceptual coup de grace of the Aristotelian worldview. And as of course you've already figured out, it's Kepler's model, having finally dispensed with equants and eccentrics, not the Copernican model that is unqualifiedly simpler than the Ptolemaic model of planetary motion. Well, as DeWitt notes, it's difficult to say anything that's both precise and true about the reception of Kepler's system. In some ways, this is because it was delivered at about the same time as Galileo's empirical discoveries, which were far splashier and easier for people to grasp and get excited about. But we know that Kepler's work was mostly ignored in his lifetime, even by luminaries like Galileo and Descartes, both of whom fundamentally agreed with Kepler's basic heliocentric viewpoint. After the publication of his major work, Astronomia Nova, Kepler had to do menial astrological work to support himself, and he died in obscurity. The Catholic Church began to weaken its practical opposition to the sun-centered view during the 1700s. But it wasn't until the early 1990s, almost 250 years later, that it officially embraced the heliocentric view, and it issued a formal apology to Galileo for his poor treatment. Though, as we'll see, the treatment was pretty humane, given how heretical Galileo's views actually were. Protestantism, by the way, was no friend to the cause of heliocentrism either. Martin Luther pronounced Copernicus to be a fool. Recent polls have shown that 20% of Americans do not believe that the Earth orbits the sun.
Crystal blue persuasion. It's a new vibration. Crystal blue persuasion. Crystal blue persuasion.